In chapter 11, we're going to be looking at what causes molecules to stay together. So we've looked at atoms in the molecule and how they're binded together, but what about a beaker of water? Why do all those water molecules stay together in that beaker? So we're going to be looking at the interaction between molecules in this chapter. And we're mainly going to be focused on solids and liquids. We'll mention gases, but solids and liquids is really what we're going to talk about. So, states of matter. Okay, so why do the different states form? What holds the molecules together? That's kind of the question. So here's some properties that we've talked about before, but gases consist of molecules that are very spread out, and they're in continuous, random, and rapid motion. Solids and liquids are condensed, right? So we know that gases are the only ones that are compressible. Solids and liquids are condensed, and we call them condensed phases. And they are in constant random motion, but they don't move around as much as gases, right? They're especially a solid. Solid really doesn't move around. It can wiggle, but it stays in place. Liquids can move around. So we're going to look at what causes these different states of matter. What causes something to be a gas or a liquid or a solid? So I have three molecules here that I'm going to draw for you. I'm just going to draw the Lewis dot structure. So we have chlorine, bromine, and iodine. So they all have the exact same Lewis dot structure. They're all halogens. And they all look exactly the same. Okay, but at room temperature, chlorine is a gas. So gas. At room temperature, bromine is a solid. And at room temperature, nope, I said that wrong. Sorry. Just kidding. At room temperature, bromine is a liquid. At room temperature, iodine is a solid. So all three of these are halogens right next to each other in the group. So what causes them at room temperature to be three different states? They all have exactly the same Lewis dot structure. So what is causing these different states? So it is these two things right here. Kinetic energy and the strength of attractive forces between the molecules. So these two things are what determine the state of matter. Determine if it's a gas, a liquid, or a solid. And so kinetic energy, we know, is that energy in motion, and it is proportional to the temperature. So if we increase temperature, we're going to increase the amount of energy, and we're going to speed up those molecules. And then if I decrease temperature, then the molecules will slow down. And then number two is the strength of the attractive forces between the molecules. So we are going to be talking about, let me get rid of this real quick. We're going to be talking about the interaction between the molecules. So this isn't the bond, this is just an attractive force right here. So this is the attractive force. Oh, running out of room there. So the interaction between the molecules, that's what we're looking at. Okay, so in gas molecules, the interaction is very weak, right? The gas molecules are spread out, so they're not held together. So there's a very weak interaction. For a liquid, we do have attractive forces, but we also have repulsive forces. So we have attractive forces that are strong enough to hold the molecules together, but we also have some repulsion going on, which allow the molecules to move around. So that's why when we pour a liquid, those molecules are able to move past each other because we have attraction and repulsion taking place. And then for solids, the intermolecular attractive forces are the strongest. So they're so strong that they hold the molecules in place. Okay, so the intramolecular bonds or forces, well, let's do this here. So intramolecular force is, I don't want to use blue, are covalent bonds or ionic bonds. So here's a covalent bond. So this would be the intramolecular force. Okay, so that's the bond that holds the atoms together. And then the bond that we are going to be looking at, or the interaction we're going to be looking at, is this one right here. This is the intermolecular force. Okay, so that's weaker. We'll talk more about it here in just a second, but intramolecular forces are covalent bonds and ionic bonds, and then intermolecular forces are the interactions between the molecules. Okay, so intramolecular forces are much stronger. They're very strong. But intermolecular forces are also strong. So they are strong enough to determine melting point, boiling point, vapor pressure, phase changes, all these things we're going to be looking at. We'll start with phase changes, but they're strong enough to determine those things right there. Like, for example, boiling point. So boiling point is when a liquid, or the temperature at which a liquid begins to boil. And we know at that point we have molecules moving from liquid phase to gas phase. So there has to be enough energy to break the intermolecular forces between the liquid molecules so it can move from a liquid phase to a gas phase. So that's kind of what we mean when we say, or when I say intermolecular forces are strong enough to determine boiling point. Okay, because again, we need enough energy to be able to overcome those interactions to move from liquid to a gas phase. So let's look at phase changes first. So we have, let's do endothermic first. So we're going to look at all the red lines first. So going between a solid and a liquid is called fusion. Okay, so, or melting. Liquid to a gas is vaporization, and gas to a solid, I went the wrong way. Solid to a gas is sublimation. So I want you to know those phase changes, and I want you to know if they're endothermic, or that they are endothermic. Okay, and then exothermic, we're going to go from gas to a solid, that's deposition, and gas to liquid, condensation. Liquid to a solid is freezing. So every phase change is determined by the kinetic energy and by the intermolecular forces. So there's a change in energy in the system. So if you look from solid to liquid, okay, we know that they're both called condensed phases. We know that they're pretty similar, except that liquid has some repulsion forces in it, and that's what makes the molecules able to move around. But they're still held together pretty closely, and then solid molecules are held in place. So there's not a whole lot of energy difference between solid and liquid. There is, a little bit, but they're pretty close. So it doesn't take a whole lot of energy to move from a solid to a liquid, or a liquid to a solid. And remember, exothermic processes release energy, and endothermic processes absorb energy. Okay, but then we go from a liquid to a gas. Okay, that's going to take a lot more energy to be able to go from a liquid to a gas, because the liquid molecules are basically going to have to break every single intermolecular force to get into the gas phase. Because remember, gas phase has very few intermolecular forces. So it's going to take a lot more energy to go from a liquid to a gas, or gas to a liquid. And then sublimation, which is solid straight to a gas, takes the most energy. Because in a solid, we're going to have to break every single intermolecular force in that solid to get it to a gas. So solid has the strongest intermolecular forces, breaking every single one of those to get it to move from a solid to a gas. That's going to take the most energy, is sublimation. Again, the blue Arrows represent exothermic, so those would be releasing energy. So to go from a gas to a solid, deposition would have to release a lot of energy to be able to do that. But sublimation, we're absorbing all of that energy to go from a solid to a liquid. Or I'm sorry, from a solid to a gas.